Okay, in this video, I'm going to solve the problems of the week related to week number 10. Of course, you will get the PDF file of these questions if you're interested below the same video that you're watching now. Okay, problem A. X and Y are real numbers. So X and Y are real numbers. And we know that 2x squared plus y squared plus 2xy minus 6x plus 9 is equal to 0. You are supposed to calculate x squared plus y squared. Oh, okay, if you have followed the video Algebraic Identities Lecture 2, you realize that how you can solve the problem. For example, here, I borrow one of these two x squareds. So I borrow one of them and put it here. And then I put 2x plus y close to it. My goal is to make a complete square, yes? So one of these x squared has been used here. One of them is left. And I put y squared here, and I close the brackets. Then one of these x squared, which is left, I take it and write it next to 6x, and then I have 9 at the end equals to 0. Yes? So let us double check. X squared plus x squared is the same to x squared. 2xy is 2xy, y squared, minus 6a and positive 9 minus 6x. Sorry, minus 6x and positive 9 minus 6x and positive 9. So, but then this becomes a quadratic pattern, so you can write it as x squared you can write it as x plus y to the 2, and then this can be written as x minus 3 to the 2 equals to 0. And as you saw in that lecture, this is a non-negative number because of this even power, and this is also a non-negative number because of the same reason. And then I know that the sum of two non-negative numbers is supposed to be 0. This cannot happen unless each one of them is 0 individually. So it implies that x plus y to the 2 is 0, and x minus 3 to the 2 is also 0. Yes? Okay, from here, what I can see is that x plus y is 0, which also gives me that y is equal to negative x. And from here, I realize that x is equal to 3. Okay, x is equal to 3, y is equal to negative x, so I conclude that y is negative 3. Yes? But my question mark is x squared plus y squared. Of course, x is 3, so it is 3 to the 2, y is negative 3 to the 2, so it becomes 9 plus 9, and the answer is 18. So the answer to this question mark is 18. More or less, all the problems in this problem set have the same idea. You have the sum of non-negative numbers equal to 0, then you can conclude that each one of them is individually equal to 0. Okay, so let me go to problem part B. Yes, so I can write problem part B here, the question. As I told you, you can have access to the PDF file of the question file through the link below this video. Okay, so x and y and z are again real numbers. So x, y, and z belong to the set of real numbers. And I know that x squared plus y squared plus z squared plus 75 is equal to 10 times x plus y plus z. The question mark in this case is to calculate x plus 2y squared plus 3z cubed. Yes, so that is the question mark. But of course, the idea is the same. So what I do, I multiply this 10 inside the brackets, move everything to the left, and try to make complete squares, the sum of complete squares equal to 0. This can be done very simple, yes? So x squared plus y squared plus z squared, I have 75, but let me multiply this 10, it becomes 10x, move it to the left, it becomes minus 10x. Multiply 10 here, it becomes 10y, move it to the left, it becomes minus 10y. Similarly, it becomes minus 10z, and then I have 75 left. There, it's 0. Okay, now my goal is to complete squares, so I can take x squared with minus 10x. How much do I need to make these two terms into a perfect square? 25. So I have 75. I borrow 25 of it and put it here. And then I write y squared minus 10y plus another 25 I borrow for this brackets. And then clearly and similarly, the next one is this. Yes? Okay, and then you can immediately see that this is x minus 5 to the 2, plus the next one is y minus 5 to the 2, and then the next one is z minus 5 to the 2, equals to 0. And again, the same strategy, yes? So this is non-negative. This is non-negative. Why? Because I have even powers. So this is also non-negative. So this means that if the sum of these non-negative numbers is supposed to be equal to 0, it's inevitable. All of them individually has to be equal to 0. So then this equal to 0 means that x is 5, y is 5, and z is 5. So this implies that x is equal to y is equal to z is equal to 5. Yes? Be careful. If one of these powers, instead of 2, say it was 3, then I can no longer conclude like this. Because if I have an odd power, there is no guarantee that that odd power is non-negative. It might happen that these are positive numbers and this becomes a negative number to compensate for that positive number, and the sum becomes 0. Okay, so having these numbers non-negative is crucial. Okay, so now x equals to y equal to z equal to 5, but the question mark is this combination, easy to calculate. So instead of x, I plug 5. Instead of y, I also plug 5. And finally, instead of z, the same. Okay, 5 is just 5. 5 to the 2, 25 times 5 is 50. 5 to the 3, 125 times 3, 375, yes? So if I add 5 to 375 is 380 plus 50 is 430. So that is the answer to this problem. Okay, now let us go to problem C. It's mentioned that A and B are real numbers, okay? A and B belong to the set of real numbers, and we know that A squared plus B squared, plus 2B squared, and then plus 2AB plus B plus a quarter, it's equal to 0. Under this condition, I want to find A minus B. Okay? I hope that by now you have enough experience, yes? So what is my goal? Again, my goal is to complete squares. Okay, because of this cross term AB, it motivates me that I need to make a complete square involving A and B. 1b squared is enough for me, so I borrow one of these b squareds and I write a squared plus 2ab plus b squared. So I used a squared totally, 2ab totally, but one of these b squareds is still left. So I take that b squared and put it next to these two terms. Yes? Again, this is a complete square, so this becomes a plus b to the 2. Then this is also a complete square. Can you see that? Yes. So I can write it as b plus a half to the 2 equals to 0. So let us double check. This is quadratic rule. The first one to the 2 gives me b squared. 2 times the first one times the second one becomes 2b multiplied by 1 over 2, so becomes b. And then the second one to the 2 is exactly the same. So what I have done here is actually valid. Again, this is non-negative because of this even power, and this is also non-negative because of the even power. So I can immediately conclude that what happens? A plus b to the 2 is 0, so I conclude that a plus b to the 2 is 0, which means a plus b itself has to be 0, and b plus 1/2 to the 2 is equal to 0, so it means b plus 1/2 itself is equal to 0. So this implies that b is negative 1/2. From here, I can conclude that a is negative b. Because b is negative 1/2, it means that a is equal to positive 1/2. Yes, and then my question mark is a minus b, which means 1/2 minus 1/2. So it becomes 1/2 positive 1/2, which is 1. So the answer to this problem, the question mark to this problem is actually 1. Okay, let us go to the next problem. So problem D. So what I have is, again, x, y, and z are real numbers, and my question mark is actually all of them. I want to determine x, y, and z individually under this condition. 5x to the 2 plus 4y squared plus 9z squared, and then I have minus 4xy minus 16x plus 54z and plus 97 equals to 0. So let me double check. 5x squared. Good. I want to find all the values for x, y, and z. Of course, you know that this is the same strategy, but it is a little bit more involved, yes? For example, you see that I have a crossing term, x and y. So it means that I need x squared and y squared. So yeah, I need only one x squared, but I can use 4 of y squareds here exactly. So what can I do? I can write x squared minus 4xy plus 4y squared. So let us see. I totally used everything here, minus 4xy. I totally used 4y squared, so that's also totally gone. But I had 5x squareds. Now I have only used one of them, so 4 of them is left. So there are 4x squared left. Okay, now what can I do? I can take this 4x squared and this minus 16x, and I can factor 4 out. So what is left for me is x squared minus 4x. So let me put an empty space in front. So be careful. I have used all my x squareds, yes? 4 times x squared. So that is totally gone. Now, 4 times minus 4x is again minus 16x. So that is all also gone. Everything is used. But what is left now? 9z squared and then 54z. I can factor 9 out, and then this is z squared plus 6z, and then let us leave an empty space and then put equal to 0. Of course, 97 is still left. We need to consider that as well. But to make this a complete square, you immediately see that I need a 4. But be careful. When I add a 4 here, because of this 4 outside the brackets, 4 times 4 is 16. So it means that I have used 16 units of this 97. So what is left for me is 81. And the good point is that what makes this one a complete square is 9, yes? So I have to add 9. But again, when I add 9 here, because of this 9, 9 times 9 is 81. So 9 times 9 is 81. 4 times 4 is 16. 16 plus 81 is exactly 97. So nothing is left. So what you see here is another arrangement of what I had here, but in a nice form, yes? Because all of them now are complete squares. So this I can write x minus 2y to the 2 plus 4 times x minus 2 to the 2 plus 9z plus 3 to the 2 equals to 0. Okay, but again, this is non-negative. This is also non-negative. This is also non-negative. Why? Because, for example, here, x minus 2 to the 2 is non-negative multiplied by 4, which is a positive number, is still non-negative. And the same scenario here. So it means that each one of them, the sum of 3 non-negative numbers is supposed to be 0. This cannot happen unless each one of them is 0. For this one to be 0, it means that x minus 2y itself has to be 0. Yes? This one to be 0, x has to be equal to 2. And for this one to be 0, z has to be equal to minus 3. So x is 2, z is minus 3. And then what I have, let me double check. Yes, everything is right. And then x is equal to 2 here. Then it means that 2y is equal to x. X is 2, 2y is equal to x. So y is equal to 1. So my answer is x equal to 2, y is equal to 1, and z is equal to minus 3. So these are the numbers that you're supposed to get for question number D. Okay? Now let me go to problem number E. Okay, so E. Find the real numbers x, y, and z from this equation. Again, I have one equation, so my question mark is to find x, y, and z, but I have one equation. The equation is x squared minus 2x plus 1 to the power of 17, and then I have plus 4x squared plus 4xy plus y squared to the power of 19, and then I have x squared plus y squared minus z to the power of 20 is equal to 0. Okay, this is also clear, isn't it? Even though this exponent is an odd exponent, this exponent is also an odd exponent, but you immediately realize that what is inside these brackets and that bracket, those brackets are complete squares themselves, yes? They themselves are complete squares. So you can write it in this form. Here you can write x minus 1 to the 2, and then you have another power of 17, okay? And then this 2 will be multiplied by 17, you get 34. So if you don't mind, let me write them compactly, yes? So this becomes x minus 1 to the power of 34. And the same here. This is 2x plus y to the power of 2, yes? The first one to the 2, the 2 times the first one times the second one, and the second one to the 2, yes? Okay, but then I raise it to power 19, so it becomes how much? 38. And then this is already an even power, so I just copy and paste it. To the 20 is equal to 0. Okay, and then again, this is non-negative now because I have an even power. This is also non-negative. This is also non-negative even powers, yes? So what can I do now is to conclude that each one of them is 0. So x minus 1 is 0. This means that x is equal to 1. This one is 0. So I don't need to write 38. It's clear that this is equal to 0 if and only if 2x plus 1 is equal to 0, yes? But x is equal to 1. If I put x equal to 1 here, then I get y is equal to minus 2. And then this one is also 0, so this means that x squared plus y squared minus z is equal to 0. But x is 1, 1 to the 2, minus y is minus 2 to the 2, minus z equal to 0. So that is 4 plus 1 is equal to 5. So if I move z to the right, z becomes 5. Yes? So x is 1, y is minus 2, and z is 5. Okay, let me go to the next problem. Problem F. Find the x, y, and z again. So we are supposed to find x, y, and z from this equation now. The equation is 4x squared plus z squared minus xz, yes. And then I have plus 9y squared plus 1. Then I have minus 12y plus z. And finally, I have plus 7 equals to 0. Okay, of course, the strategies are all the same, but you need to practice to be comfortable with these kind of tricks. Okay, what we can do. Okay, so the only thing that I can think about is to multiply these numbers, yes? So let me multiply to see how is it going. So it is 4x squared plus 4z minus 4xz, yes? Let me multiply this 9 here. So this becomes 9y squared, and I will have plus 9, and I have a 7 at the end. So if you don't mind, let me write 9 plus 7, 16, yes? So 9 times y squared, 9 times 1, and plus that 7 is 16. And then I will have minus 12y minus 12z, and this is equal to 0. Okay, clean this. Okay. So again, I see that I have a cross term between these two variables, x and y. So both x and z. So both x and z has to be involved for one of the complete squares at least. Yes. So what can I do? So I will. Yes, I need 4 of them with that one. Okay, so I will do like this. I will take 4x squared minus 4xz. Yes. okay? But I already used everything here. I also use that one, but I only use one of them. So let me write z squared here, okay? And this is a complete square, yes? I hope that you can immediately see that. What is left for me? There are 3 z squareds left for me here, okay? But then this one and this one, I can take a 3 out. So then it becomes 3. I have z squared minus 4z. So let us put an empty space in front. So it means that I already used everything here, and I also used everything here. Okay, what is left is 9y squared minus 12y. So let me write both of them in one brackets here, and then let us adjust everything. Remember, I have still 16 left. Okay, this is already a complete square, but for this one to be a complete square, what I need is a 4. But this 4 is multiplied by 3, it means it is 12. So I have used 12 out of this 16. Okay, so 4 is left for me. I put 4 here, and then on the right hand side I have 0. Okay, this is easy to see. It's a complete square. You can immediately see that, yes? So it is 2x minus z to the 2. This is 3, and what is inside the brackets is also very easy to recognize that this is also a quadratic pattern. But then you see this is also a quadratic pattern, yes? Can you guess? I can just write it as 3y minus 2 to the power of 2. So let us double check. This 1 to the 2 is 9y squared. 2 times the first one is 6y. Multiplied by the second one is negative 12y. And then the second 1 to the 2 is 4. So everything is in order. And then everything becomes clear again. So this means that non-negative, power 2, even power, non-negative, non-negative. So each one of them has to be equal to 0. So this gives me that 2x has to be equal to z, and z has to be equal to 2, and 3y should be equal to 2. So this means that y is equal to 2/3, and z is equal to 2. And then 2x is equal to 2, so it means that from these two I can conclude that x is equal to 1. So x is 1, y is 2/3, and z is 2. Okay, let me go to the next problem, G. Okay, G. What I have is x to the 3 minus square root of 2 totally to power 10. And then I have x to the 18 minus 4y to the 20. And then I have x to the 6 plus y to the 2 minus z totally to the power of 30 is equal to 0. But the question mark is only for z. I am supposed to find the numerical value for z. Okay, but this is already in a good form. All of them have even powers, so all of them I can immediately realize that are non-negative and the sum is equal to 0. Same strategy, yes? So non-negative, non-negative, non-negative. Why? Because powers are even. Okay, so then this has to be equal to 0. For this expression to be 0, I only need to, this is necessary and sufficient that the base is equal to 0. So x to the 3 has to be square root of 2. Yes? This means that x to the power of 18 is equal to 4y. Yes? And this means that x to the power of 6 plus y squared is equal to my unknown z. And then the conjunction is and. Okay, so let us see. If I want to calculate z, I need to know x to the 6, y to the 2. Yes? X to the 6 is easy to calculate, yes? Because x to the 3 is square root of 2. So x to the 3 to the power of 2 is the square root of 2 to the power of 2. Agree? And then this gives me x6 is equal to 2. Okay, so good. I know that x to the power of 6 is 2. But what about y to the power of 2? For finding y, I need to know x18. Okay, so this time I raised both sides of this to the power of 6 to make x18. Yes, so what I mean is that x to the 3 to the power of 6 is the square root of 2 to the power of 6. But what does it mean? This is x18, 3 times 6. But the square root of 2 to the power of 6 is 2 to the power of 3, which is 8. So this means that x18 is 8. Okay? So now I can use it here. x18 is 8. So I put 8 here. It becomes 8 equals to 4y. Then I can immediately, by dividing by 4, I realize that y is 2. Now everything is in order. So z, which is my question mark, is equal to x to the 6 is just simply 2. So then it becomes 2 plus y is 2, but I have y to the power of 2, so it becomes 2 to the 2. And this is 4 and 2, this is 6. So what I get here for z is simply 6. Okay? I go to the next problem now. So h. A, B, and C are real numbers. Our condition is this. I know that 2 times the sum of A and B and C is equal to A squared plus B squared plus C squared plus 3. I am supposed to calculate this expression, A to the 10 plus B to the 10 plus C to the 10. This is wanted. Yes? So what I do is this. The algebra is simple, so let us do it immediately. I multiply 2 inside and move everything to the right-hand side. A squared is already there, B squared and C squared and 3. 2A, I move it to the other side, it becomes negative 2A. Same reason, negative 2B and negative 2C. What is left here is 0. But then you can immediately realize that this 3 can be written as 1, 1, 1 plus 1 plus 1, and I complete the squares immediately. A squared with minus 2a with one of these ones is a complete square. And then I have b squared minus 2b plus 1, and then similarly, this one is equal to 0. Yes? I think it's very simple now. This becomes a minus 1 to the 2 plus b minus 1 to the 2 plus c minus 1 to the 2 is equal to 0. Even powers, non-negatives, the same story. So it means that a is equal to b is equal to c is equal to 1. And then my question mark is a to the 10, which is 1 to the 10, plus b to the 10, plus c to the 10. But all of them are 1. 1 plus 1 plus 1 is 3. So that is also simple. But let me go to the other problem. Okay, so I go to problem I. this is more interesting. X, Y, and Z are given positive real numbers. So X, Y, and Z are real numbers. And of course, it is mentioned that all of them are positive. Okay? And I know something. I know that the sum of these three numbers is equal to the square root of x times y under the square root sign plus square root of y times z plus square root of z times x. This is given, and the question mark is this, is square root of x plus square root of y plus square root of z to the 6 divided by 6 times x times y times z. Okay. Of course, I can make this squares complete again, but usually if you want to be successful in mathematics, you need to be able to use the theorems effectively. If you have already watched my lecture, Algebraic Identities Lecture 2, I actually teach a theorem there. So let me just tell you the content of that theorem. In that theorem, I show that if a squared plus b squared plus c squared is equal to ab plus bc plus ca, you can immediately conclude that a is equal to b is equal to c. Okay? This is what I showed there. How I did that, I just multiplied everything by 2, moved these things to the left-hand side, and made 3 complete squares and used the same strategy so far. But my point is that, of course, I want you to use the theorems. You need to improve this ability that you can use the theorems effectively. Otherwise, you have to solve all the problems from scratch every time, which is probably not very efficient. Okay, so this is my goal. I want to use this theorem that I told you there to solve that problem. Okay, so what can I do? By the way, you can interpret it in a different way. I can say what is this inside this box to the 2, what is inside the circle to the 2, plus this to the 2. If I have this pattern, which is this, uh, uh, yes, if I have this pattern, I can immediately conclude that what is inside the box is equal, what is inside the circle is equal to what is inside my triangle, okay? So let us keep this one. This is the content of my theorem. Okay, now the trick is that if I want to use this theorem effectively, I do some trick. I would say that let square root of x be denoted by a. So you see, if you forget about the theorem, I have x and y and z as my variables in the theorem, in the problem. So now I am introducing new variables. I say that name square root of x by a, square root of y by b, and a square root of z by c. Okay? So then this means that x is a squared. If I raise both sides to power 2, then x becomes a squared. Then this implies that y is b squared. And then this implies that z is c squared. Okay? Clear? But then I have this relation. I can rewrite that relation in terms of a, b, and c this time. Instead of this x, I will say that this becomes a squared, that y becomes b squared, and then similarly c squared. But then you see that this square root of x times y can be written as square root of x times the square root of y. The square root of x is a, square root of y is b. So then it becomes a times b. Similarly, this becomes b times c, and the other one becomes c times a. Okay, this becomes, so this is the new way of writing the same expression, but in terms of my new variables a, b, and c. On the other hand, This question mark can also be written in a new form. So the question mark is equal to square root of x is just simply a. Square root of y is b. Square root of z is c to the power of 6 divided by 6 times x, y, and z. X is a squared, y is b squared, c is c squared. So this becomes 6a squared, b squared, c squared. But on the other hand, you immediately see that I can use this theorem. Yes, this implies that A is equal to B is equal to C. If I put this information back here, then it becomes A, B, and C are all the same, so I can write A plus A because B and C are also equal to A to the power of 6. And then I have here 6A squared. Instead of B squared, I can write A squared and again A squared. But this becomes 3A to the power of 6, and then I have 6A to the power of 6. A squared times A squared times A squared. This becomes 3 to the power of 6, A to the power of 6, divided by 6A to the power of 6. But then this A to the power of 6 and this one are cancelled, so I get 3 to the 6 divided by 6. I can write it as 3 times 3 to the 5 divided by 6. This 3 and this 6 are simplified, so I get 2 in the denominator. And I remember that 3 to the power of 5 is 243. And if I divide this by 2, it becomes 121.5. Yes? So you see that I could, in principle, not use this theorem. I do everything from scratch. So it means that I am doing the proof of the theorem in the problem itself. Of course, that's also completely okay. But I would say that sometimes it's better to learn. You need to train yourself so that you can use the theorems effectively. Okay, so that is the answer to that problem. For example, again, let us go to the other problem. For example, I can solve this problem in two different ways. I want you learn what I mean. Okay, so here I go to problem number J. Let us solve this problem, for example, normally first, not using the theorem. Okay, so the question tells you that a squared plus b squared plus ab is equal to b minus a minus 1. And I am supposed to calculate a to the power of 101 plus b to the 101. This is the question mark. Okay, so assume that I don't want to use the theorem. I can calculate this, but if you want to solve this, you need to recall what was more or less the proof of the theorem. So in that proof, if you realize, I multiplied everything by 2. So let us do that here. So I multiply everything by 2 and move everything on the right-hand side to the left-hand side. So let us do it in one go. So then it becomes 2a squared plus 2b squared plus 2ab, and then it becomes minus 2b plus 2a plus 2, yes, equals to 0. Okay, and then what I do, I write a squared plus 2ab plus b squared next to each other. So remember, I used one of these a squareds and I used one of these b squareds. Okay, so what is left now? I have a squared left. Now a squared, it's finished. And then I have positive 2a, and I use one of these numbers here, 1. And what is left? I have 1b squared left. I have minus 2b here. And then what I have, 1 left here, yes? Okay, let us double check. A squared, 2a squared. B squared, 2b squared. 2ab, 2ab. 2a, 2a, minus 2b, 2b. 1 plus 1 is 2, so that's okay. And then the same story, so this becomes a plus b to the 2 plus a plus 1 to the 2 and plus b minus 1 to the 2. So then what happens? it means that this is 0, this is also 0, this is also 0. So this means a plus b is 0 and a plus 1 is 0, which gives me that a is equal to -1 and b minus 1 is also equal to 0. This gives me b equal to 1. By the way, there is an and here and here. So let me tell you something. If, for example, if you just consider these two equations, of course, you can get your a and your b. But it doesn't necessarily mean that you've solved the problem, because you have to also check the first equation. If this is supposed to be a plus b equal to 1, then I would say that there is no solution for this. Yes. So, but here it is consistent with these two conditions. This is the meaning of and. They have to happen simultaneously. So a is -1, b is 1, and then if I add a plus b, this is indeed 0. So everything is consistent. A is equal to -1, b is equal to 1. My question mark is what? A to the power of 101 plus b to the power of 101. So -1 to the power of 101 plus 1 to the power of 101. But because 101 is an odd number, -1 to an odd number is -1. This one is 1. Then if I add them, it becomes 0. Okay, so you see that I haven't used the theorem and it was not hard, but I want you to learn how to use the theorems. Okay, so if I want to use the theorem, this theorem for the solving that problem, you need to be a little bit observant. Okay, so what I do, I rearrange this in a way that I can use this. But you see that in order to be able to solve the problem using this rule, I need to have the sum of 3 squares. Okay, so let me write everything from beginning. So I have a squared, b squared plus ab is equal to b minus a minus 1. Okay, I already have two complete squares, a squared plus b, so far so good. But then I move -1 to the left, it becomes +1. What is the motivation? Because 1 can also be assumed to so be viewed as 1 to the 2. So that's also a complete square. So let me move that one to the right. So then it becomes AB, and then I have plus B minus A. Yes? No, sorry. This AB to the right, it becomes negative AB. But if you are a little bit observant and experienced, of course, you can immediately realize that this can be written in this form. A squared, instead of b squared, I put minus b to the 2. Is that okay? Minus b to the 2 is the same. You need to wait a little bit to see why it works. And then instead of 1, I put -1 to the 2. That's also correct. Yes? Okay. But then here, instead of minus AB, I write A times minus B. Instead of B, I write minus B minus 1. And instead of minus A, I would write A times minus 1. Yes? And I hope that you can realize the pattern, yes? So if I take this as my box, if I take this thing as the circle, and if I take this thing as my triangle, the left-hand side reads box to the 2, circle to the 2, triangle to the 2. Exactly. But then let us see what happens here. A is your box, minus B is your circle. So box, circle, box, circle. And here, this is your circle, this is your triangle. So box, triangle, sorry, circle, triangle, circle, triangle. And then here what you have, A is your box, yes, and this is your triangle, yes. So by considering this as my box, as my circle, as my triangle, I can actually get the pattern exactly back. So then, according to that theorem, this means that what is inside the box is equal to what is inside the circle is equal to what is inside the triangle. But what is inside the box is just A. So it means that A is equal. What is inside the circle is minus B. And what is inside the triangle is minus 1. You see, A is equal to minus 1, minus B is equal to minus 1. So this means that A is equal to minus 1, but B is equal to 1. And these are exactly the same answers that we got just doing everything from scratch. Here, both of them are actually completely valid. But I wanted you to know that if you know the theorem, sometimes many questions can be reduced to what you know as theorem. This is something that if you want to do mathematics, you need to improve, okay? This is a very vital skill. Okay, now finally, the last problem might be the more challenging one, but of course, I don't think it is very hard now. You know the trick. The trick is more or less similar to here, introducing new variables as A and B and C. Okay, so let us do this. K. So x, y, and z are positive real numbers. So let us write that x, y, and z are all positive numbers. All of them are real numbers. And I know something. I know that x times y plus 1 plus y plus y times 1 plus z plus z times 1 plus x is 6 square root of x, y, and z. And then I am supposed to calculate x squared plus y squared plus z squared. This is my question mark. Okay. So I don't know. This is more or less similar to that trick. So I think because working with the square roots for our brain is a little bit harder. So sometimes introducing new variables to get rid of square root signs is a good idea. So if I want to do that, I can do the same thing again. So what? I can introduce, I would say let square root of x be denoted by a, square root of b, square root of c, a square root of y be denoted by b, square root of z be denoted by c. And again, as before, x is a squared, y is b squared, and z is c squared. So let me rewrite this expression once more. Yes. Instead of x, I put a squared, and then I have 1 plus b squared, plus. Instead of y, I put b squared, and then I have 1 plus z squared, z is c squared. And then z again is c squared, 1 plus x, which is a squared. On the right-hand side, you see that this can be written as a square root of x multiplied by square root of y multiplied by square root of z. Square root of x is a, this is b, this is c, so it is 6abc. Yes, I don't know. From psychological point of view, this is easier to see than that expression. Yes. So what can I do? I multiply this a squared and everything inside, so it becomes a squared plus a squared b squared. Yes, and then I have b squared plus b squared c squared, and then I have c squared plus c squared a squared, and I move minus 6abc to the left. The reason is clear, because my strategy is still the same. I want to have the sum of complete squares. Okay, but how can I do that? Here, I don't know, can you see that yourself? I have a squared here. I take it with this one, but I split this into 3 equal pieces, minus 2abc, minus 2abc, minus 2abc. Yes? And then more or less the idea becomes clear. So I take a squared, and then I take one of these minus 2abc's here, and then I put b squared c squared here. Yes? And now I hope that you can do this, the rest of it yourself. Yes? This becomes b squared. So let us see what I have used. I used a squared. I used one of these minus 2abc's. I used bc squared, b squared c squared. So I start with b squared. Then I go and, for example, write one of these minus 2abc's again. And then this time I would write c squared a squared here. Okay, so I use this one, I use this one, and I use this one. And then what is left over, I put them in a separate brackets at the end. So what happens, this is c squared left. Let me write them in a disciplined way, in a tidy way. So c squared, and then what do I have here? It's minus 2abc left. And then what is left here now is a squared, b squared. So let us double check. C squared I used, minus 2abc, the last one I used, a squared, b squared I used. So nothing is left. And on the right-hand side, I have 0. But then I hope that you can immediately recognize the quadratic pattern, yes? So the pattern is clear now. You can think about the pattern while I am erasing the board. Okay, could you get it? So here, this becomes a minus bc to the 2. Let us double check. The first one to the 2 is a squared, yes? 2 times the first one times the second one exactly gives you minus 2abc, and the second one to the 2 is that one. Then you immediately realize that what I have, the other one can be written as b minus ca to the 2, and the other one can be written as c minus ab to the 2 equals to 0. Okay? The same strategy. Non-negative numbers, the sum is 0. Each one individually has to be equal to 0. So this means that A has to be equal to BC, because if this is going to be 0, this has to happen. The same thing here. So I would write and. B is equal to CA, and a C is equal to AB. Okay, so sorry, the charge of my AirPod was finished, so I had to wait a little bit. So, okay, so we got up to this point, and I realized that A is equal to BC, B is equal to CA, and C is equal to AB. And then my question mark is x squared plus y squared plus z squared, but x squared is a to the 4 because x is a to the 2, so x to the power of 2 becomes a4. So my question mark is actually a to the 4 plus b to the 4 plus c to the 4, yes? So that's my question mark. If I want to get this combination out here, so this motivates me to multiply both sides by a to the power of 3. Then this becomes a to the power of 4 is equal to a to the power of 3 bc. This implies that b to the power of 4, by multiplying both sides by b to the 3, it becomes a b to the 3 c. A is the same A, C is the same A, I multiplied by B3. And the same thing here. So C to the 4 is A, B, C3. And then because the question mark is the sum of these numbers, it motivates me to add both sides. So it becomes A to the 4 plus B to the 4 plus C to the 4 is equal to this thing plus that thing plus that thing. But all of them share ABC. Yes, so I take ABC out, then I am left with a squared from the first one, b squared from the second one, and c squared from the last one. Okay, so to be able to answer a4 plus b4 plus c4, I need to be able to answer this one and that one. But that's also very simple, yes? How? Here, if you multiply everything here, this becomes ABC. On the right-hand side, I will have two a's, so it becomes a squared. I will have two b's, it becomes b squared, and I will have two c's, it becomes c squared. So then it means that ABC is equal to ABC to the 2. I have a number which is equal to its square. So either this number is 0 or that number is 1. But the number cannot be 0, because if this number is going to be 0, it means that at least A, B, or C is 0. So it means that at least X, Y, or Z is 0. But X, Y, and Z are supposed to be positive numbers, so it is not possible for this product to be 0. So the only thing that's happening is that ABC is equal to 1. Okay? So ABC in this is 1. Now, let us calculate that one. I need to calculate a squared plus b squared plus c squared. With the same motivation, I want to have a squared. So I multiply this by a. It becomes a squared. On the right-hand side, it becomes abc. But what is abc? abc is 1. I multiply both sides of this by b. It becomes b squared. This becomes abc. But again, ABC is 1. And for the same reason, C squared is ABC, which is 1. So if I add them, A squared plus B squared plus C squared is 1 plus 1 plus 1 is 3. So this one is also 3. So if I want to calculate this, I need to multiply them. So then the answer becomes 3. Okay. Once more, I will put a link for these questions under this video. And I really appreciate that. If you have any comments or any requests for some kind of mathematics that you might need, I will also be very happy to hear it from you. Might be I would be able to teach it, I don't know, prepare some kind of videos and upload it on my channel. Thank you very much.